Okay, so if you would for me, go ahead and make sure that you're on this slide in your solving rational inequalities notes. We're going to take our conversation from yesterday about solving polynomial inequalities and apply it then to looking at a rational inequality, a place at which we have a polynomial over a polynomial less than or equal to 0 in this case. So a couple things that we want to note, because it's one of the things that we've talked about the most, is this idea of what it means to have a restriction for a rational expression, really. So, we're going to start by looking at x minus 5 and clarifying, okay, in that denominator, what is my restriction? So off to the side, I just want you to get in the habit of listing that restriction right away, clarifying x cannot equal 5. And immediately, we're going to start to just have in our head this idea of what it is that we're graphing. Just really quickly, without even doing any type of test at all, any even limit test, we could say, oh, look, this is an expression, and if we graphed it as an equation, it would have a vertical asymptote at 5. I would have an x-intercept, we should know there, at -1. And if you wanted to, you could quickly test the left and right side. You could put in, if we wanted to take the limit of this expression as x approaches 5 from the left, you could put in 4.9, that'd be positive over a negative. So this would be down here, which would make sense because I've got a -1/5 for a y-intercept. My horizontal asymptote is 1. Obviously, just I'm saying this super fast, putting together all the things we've talked about with regards to the graphing of a rational function. Because this is an expression with a factor that is raised to an odd power, based on everything we talked about Monday, we know the behavior on the other side of the asymptote is the opposite. So what we're looking for is, where is this expression less than or equal to 0? And just really quickly, we can tell, oh, okay, it must be from here to here. It's this section that is at 0 and below 0. So it becomes kind of obvious, hopefully, and if not, I'm going to state it, that what is important is not only the restriction, that's going to matter, but also the zeros. The zeros are going to matter as well. And we're going to go ahead then, and just like we did with polynomials, we're going to put these restrictions and zeros on a number line. Now, I like to do it like this. I'm going to put -1 here, here's 0, 1, 2, 3, 4, 5. And then I'm going to put up above, it cannot be that. And at -1, it is 0. So that when I go and I test these intervals, I'm aware that no matter what, whether this is a vertical asymptote or a hole, whether this is a vertical asymptote or a hole, it can never be 5. So I essentially have 3 intervals that I'm testing, from -∞ to -1, -1 to 5, and 5 to infinity. So just like with polynomials, I'm going to throw in test points. So let's say in this interval right here, when my x is less than -1, I'm going to throw in the number -2. That's my actual test point. When I put that on top, -2 plus 1 is negative, and on bottom, -2 minus 5 is negative. So a negative divided by negative is a positive. So this interval, go. Very awkward. This interval is going to be positive here. Now, after I have tested less than -1, I'm going to then test between -1 and 5. Now, it would be great if the smartboard would add a positive there, so we knew that that was positive. I'm going to pick then a number between -1 and 5. So I like to list this. You could even do it in interval notation if you wanted to. And whenever I can, I want to pick 0 because it just makes life easier. This is a positive on top, a negative on bottom. So a positive divided by a negative, is negative. So this chunk right here is negative. I then pick a number greater than 5. So let's say I go with the number 6. I put 6 in. 6 plus 1 is positive. And I'm dividing by another So my actual answer to this rational inequality is from -1 to 5. It is the interval from -1 to 5, which should make sense. -1 is where it hits and then extends down in the negative infinity direction. So obviously those are all, this is going to approach that asymptote, those are all negative. And then at 5, it stops because it is not defined at 5, and then picks up again in the positive, on the positive side of things, on the other side of the asymptote. What I'd like you to do is go ahead and look at your next example here. 2x plus 1 over x plus 3 times x minus 1. And I want you to just hit pause long enough to name the 0, name where it's undefined, and then go ahead and make a sign chart after putting those on that number line and determine where is this r of x positive and where is it negative. Go ahead and hit pause for a minute and then come on back. So the 0 is hopefully obvious. We're getting that from the numerator, and since the denominator is already factored, I know that my x cannot be -3 and x cannot be 1. When I go to put these on a number line, and I'll fill out those answers here in a minute, I'm just going to remind you what I said on that previous slide. I like to put a big fat X there so that I do not try to make that an answer. Obviously, just from glancing, I can tell that's going to be an asymptote. I've got a 0 at -1/2, and at 1, just again, based on the fact that I have a factor that doesn't cancel, I've got another vertical asymptote. Now, I'd encourage you, if you want to throw this into your calculator just to see it graphically. We actually kind of have a clue a little bit for what it looks like here. I now have 4 different intervals that I want to test. I'm going to try to change color here. I apologize for the awkward slowness. My intervals that I'm testing are from -infinity to -3, -3 to -1/2, -1/2 to 1, and 1 to infinity. I've got those 4 intervals that I am testing. Now, I'm going to say this kind of quickly. If you would like to create the table the way we created on the previous slide, you can do that the way we created on the slides regarding polynomial inequalities the other day. That's fine. We can take -4 and plug it in. When I plug it in, this becomes negative, this is positive, this is negative, and this is positive. I chose -4 in that first interval. -1 or -2 is pretty easy in the second interval. I love choosing 0, so when I choose 0 here in this third interval, that's going to be a positive on top, a positive, and a negative on bottom, thus resulting in my negative expression. Then I can pick an easy number. Usually the far right one is the easiest, besides picking 0. When I answer the positive question, this is going to be -3 not inclusive. That's why putting that X is a good reminder. Up to -1/2 also not inclusive. Now, this has to be not inclusive because I'm specifically asking for when it's positive. The previous example asked for when it's less than or equal to 0. Positive is not equal to 0. It is also positive from 1 to infinity. This is negative from -infinity to -3, and from -1/2 to 1, all non-inclusive. If you'll go to the next one, there are a couple things that I want to just comment on, and then I'm going to have you try it. I want to emphasize some of the things we talked about yesterday. We cannot do any test point method until I am in all factored form, or unless I'm in one singular fraction. Those are my 2 options. So as is, this is not okay. I cannot leave this and begin to solve. So what I'd like you to do is think of this as kind of a checkpoint to see if I'm adding or subtracting rational expressions properly. And then when you're ready, I'm just going to rattle through the work. You can come back, hit pause for a minute if you would, and come back and check to make sure that you're adding and subtracting this properly. Okay, I'm going to go ahead and have a common denominator of x plus 3 times x minus 1. I'm going to proportionalize, it's my word, not a real word. I'm going to proportionalize 5 with x minus 1 and 3 with x plus 3. I'm going to then have x plus 3, x minus 1 in the denominator. And on top, when I simplify this, it becomes 8x plus 4. That's from 5x minus 5 plus 3x plus 9. That simplifies to 8x plus 4. Now, hopefully, as you start to get the hang of this, you're starting to recognize that what I'm looking for are two things. And my suggestion would be to get in the habit of listing the zeros, but because I have a rational expression, I'm also looking for those restrictions. My suggestion, hit pause, list those, put them on a number line, try to come up with your number line, and then come on back. My zeros in this case are -1/2, as well as my restrictions, which are x cannot be -3 and 1, sounding similar to that front problem. What I want to emphasize then is we're going to put these on a number line. And again, I've got -3. I've got that vertical asymptote. I can put an x there too if it helps. -1/2. These numbers purposely are similar because you should hopefully get a feel for this now, that really the only change is that I had to do these first couple steps to get to this point. You'll notice how close that numerator is to the previous numerator. When I tested this, I got negative, positive, and then I am simply solving this time for where this is less than 0. So instead of listing both the positive and the negative, I'm listing only when it's less than 0, which is from -infinity to -3, and from -1/2 to 1. Now I want to also comment on the fact that what you should notice here is that with each of these, we have looked at what happens when one side of my inequality is 0. And I want you to go to the back page, and I want you to look at what is tonight's homework, which is the rational inequalities. And I want you to look specifically at number 5 in the sample problems, where I have 2t plus 7 over t minus 4. And I'm going to help you get this one started, and then I'm going to ask you to use this as an opportunity then to, after we do the final problem, pause and then start working on the homework for this. There should be something that catches your eye right away about why this problem is different. Ideally, what you notice is that this one side of this inequality is 3. One side of this inequality is 3. And I want to draw your attention to our conversation that we had yesterday. And that the reason that that test point method works is several things. One, it is those polynomials that we found inequality expressions or intervals for were in factored form, number 1, but it was also based on the fact that we were comparing to 0. So when I see this big fat 3 on the side, my gut must tell me that that is not okay. Oops. That it is not okay to leave that 3 on the right-hand side. I need to get it to the left-hand side. And then what I need to immediately do is use the exact same steps that we did in the previous problem and recognize, okay, I solved one problem. One problem is that now one side is equal to 0, but now I have a second problem. And that second problem is that I have to get this into a common denominator and a singular expression so that then I have simply a fraction greater than equal to 0, which then I can solve. My common denominator of t minus 4 would tell me that I could keep that 2t plus 7 on top, but I must proportionalize that 3 with a t minus 4. I'm going to give the smartboard a second to catch up. I apologize for the delay. You might want to just fast forward for a second until you can get to me writing again. And then once there we go. We got 2t plus 7 minus this proportionalized numerator here, 3 times t minus 4 over t minus 4. And now once I simplify, I can follow the exact same steps that I followed before. Last quick comment, I'd like you to flip back if you would. That'll help you with number 5 on the homework, by the way. Flip back for a minute to the interesting example with a twist, where we have both a combination of polynomial and then a throwback to algebra 2, in which I actually have a square root, which is just a heads up. It allows us to then look at rational expressions that have their own twist to them with radicals. Obviously, the 2 rules that we keep sticking to are, where are my zeros and where are my restrictions? So I want you to see in advance how, if I just give you some quick tips, you actually really do know how to solve this. So I'm going to ask you, go ahead and hit pause, name the zeros and the restrictions. Okay, x equaling 3 is a 0. If I stuck in -1, actually, into here, if I wanted to know when x plus 1 would equal 0, x would equal -1. Those 2 numbers are zeros. I can put those on a number line. But then perhaps the trickier part is the restriction. And a reminder, you cannot take the square root of a negative number. So x plus 1 must be greater than or equal to 0. So x must be greater than or equal to -1. So when I go and look at -1 and 3 on my number line, I know that x cannot be, or could be 3 as a 0. It could be -1 as a 0, but then it must be this and up. So in reality, here's how we address this. If my restriction says I have to be from here up, I cannot be down here. So therefore, I only have 2 intervals to test. So I test here I'm going to pick the number 2 here and the number 4 here. Obviously, I can pick 0 here as well. 2 minus 3 is negative. The square root of 3 is positive. A negative times a positive is a negative. If I pick the number 4, I can do 4 minus 3 is 1. That's a positive. 4 plus 1, square root of that is positive. This is positive. I'm looking for where this is greater than or equal to 0. So perhaps one of the more interesting parts of this is the actual answer. The solution, most people would say quickly, they'd be like, oh, got it, from 3 to infinity. Just don't forget. At -1, this function or this expression, the complicated expression on the left, can also be 0. So this is -1 combined with 3 to infinity. All right, your actual assignment is posted on your form that I gave you yesterday. It tells you exactly what you need to do tonight. So video 1 is complete.